I'm going to do my best not to break into song here with this microphone, even though I really kind of want to now. I might, no promises. So I am Beth Stone, the collections conservator with the University of Iowa, and I work with probably half of you. So most of you will know what I do, and these slides will look familiar to you. Thank you for coming out tonight. I don't know how many of you, I know at least one of you was competing for your attention with Caitlin Clark in her first WNBA game. So no spoilers when I leave, because I am going to go home and watch the game. So, all right. So you can see here on the screen there is this dark green emerald book. I'm going to talk a little bit about that and the sort of the risks that books that may look like this pose. So the film that you're going to see here is way more contemplative, but I'm starting out with two kind of concrete examples of what is done on campus with some cultural collections. So my job as a conservator is really to treat the items from archives and special collections to ensure their ongoing access, because that's our goal, really. So librarians, archivists, conservators, we're not just simply collecting the items, but we want to physically preserve them, and then there are librarians, probably some of you here in this room, whose job it is to make sure that they can actually be found. So dealing with search terms and all of those things that I don't have to deal with, so thank you, colleagues. My job is really to make sure that the handling of this object is safe both for the book and for the people handling it. So many of my treatments employ really straightforward actions and tools, things that honestly when you go into any art room in K through 12 rooms would look really familiar. Things like fancy erasers, starch-based adhesives, tiny brushes, tweezers, Kozo paper, and sometimes we tint with pigment-rich acrylics. So it really sounds more like art than science. But recent projects in the field of book conservation and at the University of Iowa really reveal the way in which we rely on analytical methods to inform our treatments. So painting conservators and textile conservators really have laid a foundation for pigment identification, and there is, they use this information to inform how they clean objects, what adhesive to use, how to slow down degradation, and to discover if an object has changed in appearance. So these same methods for identification are used to identify pigments in illuminated books, which are illuminated tiny little paintings, in books. But there hadn't been a lot of research done beforehand on the cover materials and safe handling. You guys can come in, it's okay. But in 2019, a conservator named Melissa Tadone, who used to work at Iowa State but is now at the Winterthur Museum, came across a bunch of books that looked like this green one, really emerald, really rich, kind of a gem-toned hue. And it reminded her of these arsenic-laden wallpapers that she came across in conservation school. And so something kind of was like, we should actually investigate this. So she worked with a team using both Raman spectroscopy and XRF testing, and there is actually arsenic in these books. So as this research is coming out, people at the University of Iowa, including me, are like, maybe we should start to think about what's in our collections. Come on in, Adrian. And so what is really great about this project is that her findings she made public immediately. And she asked other conservators to examine their own treatments, perform testing, and she gave us parameters for that testing. in order to identify if there were heavy metals in any of our collection material. So she identified titles. We took the titles. There were about 100 that we knew we had in our collections. So we removed all of those from circulation. Don't worry, you're not going to go in and touch an arsenic book. And then we found that about a little over half of those we didn't need to test. They had either already been rebound, or they were from a different year, and so they were in a different color binding. You can see there's a little slip I'm using to compare the color. And so just by eye is how we did that initial sorting. The emerald green that did look very similar to that sample that she gave us. We had about 40 books that were then tested. We just used XRF because that's what we had. And the XRF is a handheld X-ray machine. And we did this in the lab, and don't worry, like we asked environmental health and safety to come by and make sure that we weren't just like shooting X-rays randomly at people. And it turns out actually, not excitingly, but kind of a relief that none of the volumes that we had did have arsenic in them. So I anticipate that we'll probably, with other research that is coming out, look at other heavy metals in commercially bound books from this era, which is approximately 1830 to the 1890s. So chrome and copper are other metals that were commonly used in pigments. But right now, we don't have any arsenic to worry about. If you want to learn more about this project, you'll have to take a screenshot of this website. So this is another really great project on campus that's happening, and probably some of you have already heard of it. Damien, who is in the audience, has participated in this. So if I say anything wrong, Damien, you'll just like shout out and correct me, right? Okay, great. So this is what you see this is a book.
Wrong.
What is it then? And it's going into a tiny CAT scan machine. And the goal here is to reveal either erased text material or erased print, images, or to locate text that is sandwiched between the cover and the leather material that we can't get to without really invasive conservation treatment. So this kind of imaging is done in collaboration with both conservators, curators, and then this is where I'm going to need your help, Damien, with the department on campus, which is the Iowa Institute for Biomedical Imaging, which I believe this machine previously had actually been used for cat brains.
Yes, it's a small animal
Yeah.
facility.
Small animal facility. But now they're doing books, which is delightful. And it really helps us, we're not going to have a CAT scan machine in the libraries and archives to do this work, so we really needed a facility on campus that we can work with collaboratively. And they have agreed to do it, and I'm going. And you can even, if you go to this website, I think you can request, if you have a book that you think justifies going through a tiny CAT scan machine, you can make a suggestion. But some of the material that was revealed in this was, I think, music scores that was on the spines of books, as well as wrapping paper, potentially prints, or some kind of decorative paper. So not only will it inform our treatments and how we decide to wash or not wash or house these things, but it also then can give us some more context about the book and the culture in which it originated. And I don't have now a very sly way of handing the mic over to my colleague.
I can just use this one.
I got that? Okay.
Hi, everybody. Can you hear me?
Yes.
Okay. Hi, I'm Angela Fritz. I teach at the School of Library and Information Science at the University of Iowa here, and I teach both the archives class and the digital preservation class. So I'm going to be transitioning from the great examples that Beth has given in terms of how science and the intersections of technology are making a difference in our analog and our physical-based archives and libraries to talk about some of the challenges that have to do with digital preservation and preserving our digital cultural heritage. As tonight's documentary points out, there are a myriad of challenges relating to the preservation of digital archives. For archivists, these challenges range from the growing size to the complexity to the volume of born digital collections. Digital materials are extraordinarily fragile and they're ephemeral and transient. They're also susceptible to data degradation, format obsolescence, corruption, and loss. Additionally, the ever-changing buyouts and mergers and changing terms of service provider agreements endanger our own personal digital archives, the majority of which live on proprietary platforms. In addition, there are a number of resource challenges, right? Digital preservation requires constant and intentional work at every stage of an object's life cycle. And as such, digital preservation is labor-intensive and it tends to be expensive. Given all of these challenges and associated risks, one of our primary digital preservation strategies is simply making multiple copies and storing these copies on different storage media and architectures combined with geographic distribution. This is what we call distributed digital preservation, and it has been practiced for decades because it's believed to provide the greatest risk mitigation for many of the challenges that I just talked about. In this context, archival storage is a major concern when you consider the scale and the need for preservation replication. Currently, we don't have a low-cost, sustainable option for long-term storage. Today, institutions use a combination of tape and disk storage, and this is a constant running debate in our field in terms of which is better. We're not going to be getting into that tonight. The really important point is to talk about the life expectancy of these storage media, which is very low, right? The average life expectancy for tape or disc cartridges are between 10 and 20 years. So that might seem like a long time, but in the archival context, it's not a very long time. And so as a result, archivists and digital preservationists must navigate constantly changing cycles of refreshing or rewriting data to new or next generation storage media. Currently, the sustainability of digital archives is based on the concept of, or really the expectation of continual migration. Migration to progressively higher density storage, which translates into the quest for progressively greater storage capacity, which will continue indefinitely for the future. This is why archivists are particularly excited about innovations to advance sustainable cloud-based archival storage systems. For example, there's a great deal of research being done to harness DNA as the ultimate data storage solution, which we'll hear about in tonight's documentary. But I wanted to mention the promise of innovations in the area of new glass-based archival storage technologies. Under the system, data is stored in quartz glass or fused silica. The genesis of glass-based storage really derives from physics research, specifically by scientists at the University of Southampton in the UK, who wanted to address the challenge of storing data in a media that didn't decay. Since then, Microsoft has engaged in extensive research and development for Project Silica, which has found that quartz glass can store vast amounts of cold data indefinitely. Quartz glass is low cost. It's a low-cost solution that offers natural resistance to water, electromagnetic pulses, extreme temperatures, and surface scratching. I did put a link to Microsoft's webpage if you're interested in more in-depth information about this project. But in general, the system encompasses 4 basic steps. The first step is writing with an ultra-fast laser. And it's important to note that there are permanent modifications to the physical structure of the glass. The data is written inside the glass, which makes the storage resistant to data degradation. It's unlike most other storage technologies or media in that it changes the physical structure of the media instead of really writing on the surface. The second process is reading through a computer-controlled microscope and then decoding through AI machine learning. And then when the disks are not being used, they're managed and maintained in a media storage panel. These panels, like the glass diskettes, are entirely 100% passive, meaning that they require no electricity or special climate controls, meaning that their environmental footprint is very small, which is directly in opposition to our current data centers. They're also portable, and they avoid the costly cycles of rewriting data to the next generation storage media. Now, I know what some of you might be thinking, especially since so many people in our audience are archivists and librarians. Another chapter in the history of storage media and archives, right? Tablets, papyrus, parchment, paper, wax cylinder, pressed vinyl, wire recordings, film, magnetic tape, optical discs, and now laser etched glass. However, there are major differences, I think, in this technology in that it really provides volumetric density higher than our current magnetic tapes. It's estimated that 7 terabytes can fit on one glass disc. To put that into context, it's said that one single glass disc can store up to 3,500 films or 1.75 million songs. It's estimated that each glass plate could last up to 10,000 years, which would make it the most durable archival storage media to date. Microsoft states that there are small-scale deployments that are currently being implemented, and that by the end of the decade, the large-scale volume implementations would be promising to support exabytes and zettabytes of archival data storage in the coming decades. Certainly this brings to mind many questions, but it is really fascinating to think about and to comprehend. And I think it lends to our discussion that has highlighted the intersections between science, technology, and archives that are truly awe-inspiring. At the same time, it's important to note, I think Beth touched on this in the very beginning of her presentation, that archivists, special collection librarians, and conservators, who through their own creativity, their own ethics of care and expertise, are the drivers of these future-forward implementations. It also illustrates the point that Trevor Owens makes in his book, The Theory and Craft of Digital Preservation. He reminds us that given all of our challenges, it's important that archivists, special collection librarians, conservators, and curators think like futurists. As these examples have illustrated, looking towards science and technological advances helps us to think about our work in new ways. Whether it be leveraging science to analyze our print and analog collections in new ways, or to strategize how to grapple with the challenge of digital storage, scientific advances help us to navigate our shifting roles, help us to evolve our stewardship practices, and hopefully help us to continue to build a culture of discovery. Thank you.